Hello everyone. Today we are going to analyze this frame using flexibility matrix method. In this frame there are two columns, column AB and column CD, and there is a beam BC. In both of the columns there is no load. In the beam BC we have uniformly distributed load 48 kN per meter. It is acting for the whole span. In the joint B, there is a nodal point load 12 kN. It is acting towards the right side. Height of the column AB is 5 meter. Height of CD is 2 meter. And the length of BC is 4 meter. In the point A, there is a fixed support. And in the point D, there is a roller support. In this frame, the number of unknown reactions and moments are 4. In the point A, we have the horizontal reaction, vertical reaction and movement. And in the point D, only we have vertical reaction. So totally 4. The available equilibrium equations are 3. The degree of static indeterminacy will be 4 minus 3, so that it will be 1. Let us release Vd. You can see that I have released Vd. We know the equation which is used in the flexibility matrix method. Here P will be Vd because that is the one we have released. In the point D, there is no sinking or settlement of the support. In this case, delta will be 0. We know that 0 matrix is 0. To find these two, we are going to use unit load method. We have to make sections. In this frame, there are 3 different parts, A, B, B, C and C, D. So we have to make 3 sections, one in AB, one in BC and one in CED. You can see that I have made 3 sections. This one at a distance of x from B, this one at a distance of x from C, and this one at a distance of x from D. Now let us make a table. First let us enter the members. We know that there are 3 members. For the section in DC, the origin is D. For this section, the origin is C. And for this section, the origin is B. For DC, the limit is 0 to 2. For CB, the limit is 0 to 4. And for BA, it is 0 to 5. Now let us find the moment M. We need to follow left-hand side rule. Clockwise will be negative and anti-clockwise will be positive. First, let us find the moment M in DC. Up to the section, there is no load, so the moment will be 0. Let us find the moment in CP. Up to this section, we have only the uniformly distributed load, 48 kN per meter. It is acting in the clockwise direction, so that it will be negative. We know that with the UDL, we have to multiply the distance and then the distance by 2. In this way, we will get minus 24x square. Let us find the moment in BA. Up to this section, we have the point load and the UDL. The UDL is acting in the clockwise direction, so that it will be negative, and the distance is 4. So 4 into 4 upon 2. The point load is acting in the clockwise direction, so it is also negative, and the distance is x. When we calculate this, we will get to minus 384. Let us apply this. Now we are going to find the moment small m. We need to remove all of the loads from the frame, and we have to apply unit load at D in the direction of VD. Let us find the moment in DC. Up to this section, we have the unit load, but for this load, there is no perpendicular distance, so the moment will be 0. Let us find the moment in CB. The unit load is acting in the anticlockwise direction, so that it will be positive, and the distance is x. 1 into x, it will be x. Let us find the moment in BA. Up to this section, we have only the unit load. It is acting in the anti-clockwise direction, so that it will be positive, and the distance is 4. 1 into 4, it will be 4. Using this formula, we can find delta L, and by using this formula, we can find delta. We have found delta L and delta. In this equation, let us apply both of them. Negative into negative, it will be positive. Since inside the matrices there is only one member, we can take them outside. We can eliminate EI. For VD, we will get 96.87 kilonewton. By applying this rule, we can find VA. Then by applying this rule, we can find HA. To find MA from the point D, let us take a moment about A. BD is acting in the anti-clockwise direction, so that it will be positive, and the distance is 4. The UDL is acting in the clockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. This load is acting in the clockwise direction, so it is also negative, and the distance is 5. Let us assume that MA is a hogging moment, so it will be acting in the anticlockwise direction. In this case, it will be positive. For MA, we will get a positive value. That means our assumption is correct. MA is a hogging moment. We can draw the shear force diagram directly. Otherwise, first we can draw the free body diagram. From that, we can calculate the shear force values. These are the shear force values for the column AB. These are the shear force values for the beam BC. In the column CD, there is no perpendicular load, so there will be no shear force. This is the shear force diagram. In this point, the shear force becomes 0. In the beam BC, in this point, there will be maximum positive bending moment. We can make a section in this point and find the distance. You can see that I have made a section in that point at a distance of x from B. We know that in this point the shear force is 0. Using that we can find x. Let us find the moment at A. At A, we have MA, which is acting in the anticlockwise direction, so that it will be negative. Let us find the moment at B. MA is acting in the anticlockwise direction, so that it will be negative. HA is acting in the clockwise direction, so that it will be positive, and the distance is 5. For the moment at B, we have got a positive value. That means it is a sagging moment. Now let us find the maximum positive bending moment in BC. MP is acting in the clockwise direction, so that it will be positive. The vertical reaction is acting in the clockwise direction, so it is also positive, and the distance is 1.98. The UDL is acting in the anticlockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. Finally, we will get 97.75. Using the left hand side rule, we can find the moments at D and C. Both of them are 0. This is the bending moment diagram. If we draw this diagram in the opposite directions, that is called the bending moment diagram on the tension side. Alternatively, we can draw the bending moment diagram by superposition method. Let us see how to draw this. First, using the loads, we have to draw the free movement diagram. In the columns AP and CED, there are no loads, so there will be no movement. We should not consider the nodal point to load, so only one is remaining, the UDL. Using this formula, we will get this value. Then we can draw this diagram. Using the end moments, we can draw the end moment diagram. Then we have to combine both of them so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.